Well, everyone, welcome to the non-trivial geometry and topology seminar here in Prague. So we have a very special Friday seminar today. We have a special guest, Bartosz Kwaśniewski, who's going to talk to us about C-star irreducible regular inclusion.
Yeah, thanks. And thank you, Tristan, for inviting me. And thanks all of you for coming and for having me here. So the title for my today's talk is Sister Irreducible Regular Inclusions. So Sister Irreducible Inclusion is a notion coined by Michael Roerdam last year, I guess. And I'm going to use this notion as an excuse to present some of the results from my number of papers with Ralph Meyer. So we proved some general results, and I think it would be nice to sell them to people. So I should try to apply them at least somewhere. So it will be a quite general application, but maybe still it will be interesting. So probably yep.
Oh, sorry, we need to share the screen or move the camera so we can see the slide.
So should I do something, or you should do something?
You share the screen. Okay.
So I should do something?
Yeah.
What should I do then? Change to Zoom, and then share screen, and then
the left, the left.
And then, so this means that I will need to operate this all the time. So that sucks.
Sorry.
I thought you would be doing this. Okay, so here it is. Okay, so this is the entrance slide. So probably all of you know that simple sister algebras are important. Probably Karen taught you about that. And maybe you also heard that the sister inclusions are often viewed as dynamical objects. So for me, so this is a basic starting object, is a sister inclusion. So A is a sister algebra, and B is a sister algebra, and A is a sister subalgebra of B. So I'll be interested in these inclusions where not only B is simple, but also A is simple. And in fact, every intermediate sister algebra is simple. So whenever I say intermediate sister algebra, so I have fixed sister inclusion, I mean sister algebra sitting between A and B. So just passing immediately to the title notion. So Roerdam started the systematic study of these inclusions where all intermediate sister algebras are simple. So this is a very rigid structure. So a sister inclusion is sister irreducible if every intermediate sister algebra C here is simple. So the reason for that is that in last years, a number of papers with examples of such inclusions appeared. And for us, the basic example will come from probably the cross product. So let us consider a discrete group action. So G is a discrete group on a unital sister algebra A. This acts on a unital sister algebra A. And so does everyone knows what a cross product is? I guess not everyone. So maybe I will recall briefly what is that. So any sister algebra can be represented in a faithful way on some Hilbert space. And if you have this group action on this A, we also require a unitary representation of this group on the same Hilbert space. And the action also requires the commutation relation, which looks as follows. So, or maybe I could write this like that. We have that for any G in G and A in A. So whenever we have something like that, we can consider that the sister algebra generated by this. This is a unitary representation. This is just a faithful representation of the sister algebra. And now we generate a sister algebra by these two guys. And they are related by this relation. And this relation tells you immediately that this thing will be the closure. So if you consider finite sum like this, where F is a finite subset of G and AG lie in A. So this is a linear, this will be a star algebra, and if you close it, you get the sister algebra generated by this. So in a sense, you can think of this algebra as this sums with coefficients in A parameterized by this unitary representation. And the sister algebra will be what we call reduced cross product. Provide that this representation has additional property that when we have a faithful conditional expectation, so that the map such that each such finite sum, which sends this sum to the element lying in the unit fiber. So this is a unitary representation. So A1 is, so 1 is a neutral element group. So this is just an A. So that this extends to a faithful map. Maybe you do from your algebra to A. Yeah. Which sits in this. This is what we call conditional expectation. We have a projection from your sister algebra onto the sub-algebra, which is contractive. And faithful means that it does not kill non-zero positive elements here. So this piece of data like characterizes what we call reduced cross product. You can construct it via concrete representation. And here we have like two very important examples of sister irreducible inclusions. I'm not sure whether I should go that slowly or should I? So now B is now a cross product and A sits in B as a subalgebra. So Kishimoto, this is a famous result of Kishimoto. Kishimoto proved that when A is simple sister algebra means that there are no close two-sided ideals, right? So close two-sided ideals are immediately also self-adjoint. So this is the right notion for being an ideal in the category of sister algebras. So what he proved that this is famous result that there's if this group action is outer, and the reduced cross product is also simple. So I now just write this instead of this. And outer, what does it mean? Outer means that all these elements from the group that correspond to the non-trivial element are not given by unitary from A. So they are not given by element from A. So there's like a weakest possible notion of non-triviality. So
do you mean point-wise outer here?
I mean, yeah, some people call this point-wise outer, but I mean, action is outer when it is point-wise outer by definition.
The result of Izumi is for finite group or for discrete?
Yes, Izumi considered finite groups. Yes, that's true. So Izumi considered finite groups, and Cameron Smith proved this result for the result that is stated on the slide for general discrete groups acting on a unital A. So this is important. So this inclusion is sister irreducible if and only if this algebra is simple and this action is outer. So this implication in general is not an equivalence, but so the simplicity of this does not suffice to give you this. But if you require sister reducibility, this is a much more rigid assumption. This gives you if and only if. And moreover, Cameron Smith gave this Galois correspondence. So not only that we have this characterization of sister reducibility, but also we have description of all intermediate sister algebras. So we proved that, so whenever, I mean, one side is clear. So whenever you have a subgroup of G, but you may restrict your action to the subgroup, and then this cross product of this subgroup of this restricted action sits naturally as a sister subalgebra in your reduced cross product by G. So we prove that any intermediate sister algebra is of this form. So you have a bijective correspondence between the groups, subgroups of your given group, and sister subalgebras. And these are kind of inclusions that I want to consider, but just to give you a more complete picture, let's also consider, so not only this algebra A sits in here, but also we have this unitary representation and the sister algebra generated by this unitary representation is then isomorphic to what we call the reduced group sister algebra. So also this sister algebra sits in this reduced cross product because this symmetry is discrete and unital. And so this inclusion is sister irreducible even only if G is sister simple. So we say that the group is sister simple even only. So by definition, this means that the reduced sister algebra is simple. So this is a famous notion now. And then there is this condition. I mean, so maybe I should, in order to understand it, I will just say what Amrutam and Kalanta proved. So,
Question in the chat.
yeah.
See it.
So I'm operating or you are? Sorry, can you quickly recall by words what we take as assumptions for being a sister inclusion? Okay, so a good question. So far, I do not assume anything. But here in this example, I mean, the A is unital and B is unital and the unit is the same unit. Soon, I mean, I will include this non-degeneracy assumption in what I call regular inclusions. But in general, I do not assume anything. So this is just a A is just a sister subalgebra of B in general. When I will add something, I will make it specific.
That's now to meet a stable conditional expectation.
No. No, but as you will see soon, when you add also regularity to this, then you will immediately get an expectation, even a unique expectation. These are questions which go ahead. So maybe I'm too slow. Am I? No? So Amrutam and Kalanta, they consider on the opposite a commutative sister algebra. So this is just the algebra of functions. X is compact because everything is unital in a compact Hausdorff space. And what they proved is that then this inclusion is sister irreducible if and only if so. Obviously, this has to be a simple algebra. So this means that G is sister simple. So this is trivial. And the action is minimal. And the action is minimal. What does it mean? I mean, the action is minimal, maybe the dual action. So if we have an action of the group action on a commutative algebra, which is just algebra of functions, so this corresponds to the action, the group action by homeomorphism on this space, on the spectrum, so that this dual action, say, is minimal. So this means there are no non-trivial invariant for this action open sets. So the empty set and the whole space is beyond one. So in other words, since X is compact, whenever you take an open set in X, you can find a finite number of elements in your group G, such that when you move around this non-empty open set in your space, you will cover the whole space using just a finite number of elements. So this is this result in a commutative case, and Rodman just noticed that it works in a non-commutative case, but then this minimality should be written like this. So whenever you take a non-zero positive element, then there are a finite number of elements in your group, such that when you move this element around, you will cover the whole space. I mean, the support of these guys cover the whole space. So this means that this is larger than one. And Amrutam also, under some conditions, also described these intermediate sister algebras as cross products by this G on some G invariant subalgebras of B containing nothing. I don't know. Okay, so
Can you explain his use of the phrase strongly mixing? Because
I mean, so this is just, I mean, so Rada did not give this a name, but he says that you should view it as a strong mixing. I mean, for commutative case, this is just minimality. So maybe you should call it as minimality, but there is a different notion of minimality in non-commutative case. So this is not this minimality. That is why.
But I mean, there is a notion of strong mixing in.
That is why it is also in question marks. So maybe this is not good. Maybe we should not write anything.
Okay.
So this is not a name. So this is just the way you should think of it. Maybe this is not a good way. And so another title notion is this regular. So Kumchan introduced this notion of regularity. So to generalize this from one-dimensional algebra to system algebra context. So in general, what it means that that the set of normalizers. So these are normalizers. So the normalizers are those elements that whenever you conjugate your subalgebra by them, you will end up in A. No matter in what direction you will do that. I also add this non-degeneracy condition to this definition. In some cases, it is automatic. In sometimes it is not. So non-degeneracy means when A is unital, non-degeneracy means just that B is unital and the unit is the same. But in general, this is non-degenerate. And here you have number of equivalent descriptions. So whenever this closed linear span of this thing gives you B, but by Cohen-Hewitt factorization theorem, this is just the same if you write as just algebraic product of these two guys. And people often, sister algebraists often say that A and B have a common approximate unit. So in general, I do not assume our sister algebras are unital. So every sister algebra has an approximate unit, and this non-degeneracy just says you that you can find that approximate unit which is here and there. This is the same one. Okay, so if you look at these examples, so you immediately see that the first inclusion is regular. Why? Because of this relation. You see that all these U's are normalizers. Moreover, A is always a normalizer. So this is trivial for any inclusion. And obviously, normalizers form a semigroup. So if you take a product of normalizers, you get a normalizer. So all these elements in these spaces are normalizers, and they span the whole thing. So in general, I just wrote the requirement is that this normalizer generate B as a sister algebra, but since they form a semigroup, they are closed under involution. So this condition just means that B is in fact closed linear span of these normalizers. So how is it in second case? What do you think? Do you think that this is a regular inclusion? This is a much harder question, and the answer is no, at least not in general. So these are kind of inclusions, but these are harder inclusions in a sense. Okay. Some questions? There's something in the chat. So this is what you answered this. Okay, so I will just immediately go to the main theorem. So I will now use results from a number of my papers with Ralph Meyer to give you a bazillion of equivalent characterizations of regular C-star irreducible inclusions. So this is the main theorem, and then I will try to describe all these conditions that appear here. So don't be scared. So we have this inclusion of sister algebras. We assume that they are regular, so we have lots of these normalizers. And we assume A to be simple, which is natural when we want to study sister reducibility. And then the following conditions are equivalent. So first of all, we have this, that the inclusion is sister reducible, which means that every intermediate sister algebra is simple. Secondly, this is a condition which often appears. So can I jump over there, or maybe I should, maybe I don't know. So in general, we say that A detects ideals in V, or that A has a intersection property, and the inclusion has an intersection property if for every ideal in V, the closed excited ideal in V, how to write it, I know. So if I is non-zero, then its intersection with A is non-zero. So in this sense, A detects ideals that it sees those guys. I mean, so it sees something at least. But when A is simple and A detects ideals in B, that immediately you see that B has to be simple if the inclusion is non-degenerate, because then any non-zero ideal here would need to contain A because A is simple. And so every ideal I has to be the whole B because the inclusion is non-degenerate. So whenever your A detects ideals in B and A is simple, then B is simple. So this explains in a sense, I mean, the equivalence between 1 and 2. Maybe not even in a sense, this just explains this. So this is like a trivial thing, but it is good because this condition is known and important, like without simplicity. And there is another slightly stronger condition that A supports. This means supports positive elements. So for every non-zero positive element in B, there exists a non-zero positive element in A, such that A lies below B in Kuhn's sense. Now I should probably explain this. So this means that for every epsilon, there is an element such that I can compress, we can compress this A is up to epsilon X X star, so we can compress this B to A by some element. So in particular, this guy will always sit in an ideal generated by B. And since this is arbitrary epsilon, if you have this, then A has to sit in an ideal generated by B. Which means that if A supports B, then A has to detect ideals in B. And this is super stronger property than this one. But if we have this, so we can see that 3 implies 2. And this is a condition important for studying the ideal structure. And this one is, for instance, important for studying pure infiniteness. So whenever A is simple and purely infinite and supports B, then B is also simple and purely infinite. So having this condition 3, and assuming in addition that A is purely infinite, we get that all intermediate sister algebras are purely infinite.
A supports all intermediates means that A supports all C.
Yes, so I just defined this how this work for B, but then you can replace B by C. That's the correct understanding.
Sorry,
And
question.
4 is maybe the most abstract and ugly condition, but my favorite because the periodicity is my child. So maybe I will not explain what it means. I will explain it soon. So there's this notion of a periodic inclusion, which is kind of the strongest from all these notions here, because this in a sense imply all of them. This implies that there is always this what is called a pseudo expectation. This is like a conditional expectation, but not into A, but into a larger object. I will also explain this. And we also assume that this unique pseudo expectation is faithful. So unique pseudo expectation, or in particular, implies that there is a unique conditional expectation at least one, if there is one, because usual conditional expectation is an example of a pseudo expectation. So if there is a unique pseudo expectation, there is at most one conditional expectation, and we can add another condition that says that there is a unique faithful conditional expectation. So this pseudo expectation, in fact, in this case, is a genuine conditional expectation. I'm not sure whether that's. And 6 is a notion of reducibility. So in fact, the sister reducibility is a notion that grew from this notion. So irreducibility is a notion coming from von Neumann algebras. So if you assume that A and B are von Neumann algebras, so this condition will give you that A is a factor, but not only A, but also B is a factor. All intermediate von Neumann algebras will be factors. So this irreducibility and this intermediate von Neumann factors, there's this papers on this appeared a long time ago. So this is now in fact like a sister algebraic version of this restriction. So Rodham showed that in general, for the inclusion, this irreducibility is not enough to get a sister irreducibility, but here under our assumption of regularity, these are the same. In 7, this is the notion of Cartan subalgebra. So maybe you have heard about this Renault Cartan subalgebras. So these are defined axiomatically inclusions that you can then prove that these inclusions come from twisted groupoids. And so the algebra, the small algebra there is the algebra of functions living on the unit space. So it will never be simple unless you have only one point. So you cannot apply this to this business of system reducible inclusions. But this non-commutative Cartan subalgebra, this is generalization produced by Axel, fits here very nicely. So I'll try to explain that later. And perhaps this is the best description, somehow maybe the most concrete description is that any regular sister irreducible inclusion in fact comes from a full bundle over a discrete group. So this is like this analog for this cross product. I mean, so this is a generalization of this. And the fell bundle and the group are determined uniquely by the inclusion. So I should say 2 words about fell bundles. So you don't need to know what a fell bundle is to understand what this algebra. This algebra is just G-graded algebra. So this means that we have direct sum of Banach spaces which are numbered by elements of the group, and they're closed. And this is G-grading. So this means that whenever you multiply 2 spaces, you will get the space corresponding to GH. And involution in the sister algebra is consistent with the group actions. So we get this. And here, these relations imply that the unit fiber is a sister algebra. So this sister algebra sits in here. And what else you require? You also require for this to have this faithful conditional expectation, like in the groupoid case, like in the cross product case. So, so this is just G-grading. But also this means this is a sister algebra. Maybe this is important that this is a sister algebra. Because of these relations, all of these BGs are A by modules. In fact, they are Hilbert by modules. So this implies that any G, BG, BG is I will write Hilbert A by module. So by module, this means that whenever you multiply by A from left and right, this is we end up in G. And Hilbert by module means that we have also these A valued inner products, and they are given in an obvious way. So The right one is given by this product. So eta is in BG, so psi star is in BG inverse, so BG inverse times BG lands up in B1. And the same is on the other hand. So you should, I mean, this is a way of thinking that is usually adopted. So you generalize, so the cross product is algebra associated to the action of the group by automorphism, and this Fell bundle structure is a more general thing. So you attach a sister algebra to an action of a group by Hilbert by modules. Like this, or you can think of it just grade the sister algebra equipped with this faithful conditional expectation that kills all these BGs for G equal to 1. Also, this construction up to Morita equivalence is equivalent to this cross product construction. So this is very close. So once you assume regularities, irreducible inclusions are only those here. And once you assume other conditions like separability of A, then you can assume, I didn't say what is outer here. So outer in this case, I mean, outer for automorphism, we said that this automorphism is not given by a unitary algebra, and BG is outer. Here, the Fell bundle is outer. B is outer, meaning these spaces, the collection of the spaces is outer. Even only if for any G non-trivial, this Hilbert module is not isomorphic to the trivial module A. So to this B1, fiber, the unit fiber. And so in separable case, we can replace this alterness by topological freeness. Topological freeness means that the set of fixed points, I mean, maybe I will explain it later. And this is related also to the notion, which is called the almost extension property, which was, I think, introduced by Reznikov and Naj and advocated by them. So this relates pure states on A, B. Maybe if time permits, I will describe that.
I have a question. Like, can you hear me?
Yes.
Okay, so what if you, for example, given an inclusion A inside B, already given as a Fell bundle, so then, like, for example, because I'm like the point 8, like that you stated, like says like, okay, that there exists an outer Fell bundle which represents A inside B. But can you also make it like a more strong condition, even saying that, like, for example, that if you start with a Fell bundle, like that the inclusion is already given by Fell bundle, then this inclusion is C-star reducible if and only if the original Fell bundle must be necessarily outer.
Yes, I mean, so maybe I didn't make it clear, but this Fell bundle in this group is uniquely determined by the inclusion.
Right.
So
yes, I think
I mean, so just going ahead. So this Cartan inclusions defined axiomatic by Excel, we have described them with Ralph as such inclusions coming from Fell bundles over inverse semigroup. But if your sister algebra A is simple, this inverse semigroup has to be a group, and that is why I get this nice description.
But if A is not simple, then this
then this is different. Yeah. But the simplicity of A here implies a lot.
Okay. Yeah.
And regularity, yeah, as well. Okay, so now I want.
Sorry, can I ask? Like, if you drop simplicity, do still some of these like hold true? Like,
Yeah, there are
outer
nice implications between all this stuff. So should I explain it now or?
No, that's fine. Like,
I mean, I will try to explain it in the due course. So I will start with this notion of a periodicity that I told you that this is my favorite. Maybe this is the most technical, but this is my favorite, so I should not avoid it. So in order to introduce it, let us denote by H of A the family of hereditary subalgebras. So what is a hereditary subalgebra? So this is like a generalization of an ideal. So D in B in A is hereditary. This just means that BAD is gay B. So every ideal is a hereditary subalgebra, but also you can take like this compressions by elements, and this will be more general hereditary subalgebras. But in the commutative case, hereditary subalgebras coincide with ideals and open sets. So the way of thinking about hereditary subalgebras is that these are like non-commutative open sets. So this is like a bunch of non-empty, non-commutative open sets. And then this periodicity can be defined for normed by modules. So we say that a norm by module, so we have a space with a norm and A acts from the left and from the right on this. If this condition holds. So what does it say? It says that for every non-empty open non-commutative set, you may find a function, so this A of norm 1, positive function of norm 1, which up to epsilon is moved, if you multiply from left and right, they are moved like to the orthogonal thing. So up to epsilon, this product is 0. Arbitrary small epsilon. So this is the way you should think about it. So this is quite technical. That is why people avoided it. People seen this in many other instances, but probably this is the best thing to work with if you want to have like really general results. So it originated from the work of Kishimoto, who considered like automorphisms. So let us start with this example. So when you have an automorphism of your sister algebra, then you may view this A as a bimodule where one action is just given by the multiplication and the other action is just twisted by the automorphism. And then there's a periodicity of this module appeared a lot in the work of Kishimoto and got a number of names. So it was characterized by Kishimoto by this non-triviality of Borcher spectrums. So some people call this condition spectral triviality. Kishimoto from some point started to call it proper outerness. There are plenty of names. I just kept with this short name, aperiodic. So this is closely related to this topological freeness. So whenever we have this automorphism, we have this dual homeomorphism on the spectrum of your system algebra, spectrum meaning irreducible representation with Jacobson topology. So this periodicity means just that this dual homeomorphism moves points. So the set of fixed points have empty interior. So you cannot find an open set which is fixed by your homeomorphism. And so at least this is equivalent to an A separable or close to commutative meaning type 1. But for us, it is important. This is like Kishimoto proved that when A is simple, this periodicity is in fact equivalent to outerness. And all this that is said on this example can be transferred to these Hilbert modules. So you may define this dual homeomorphism for modules because then they are equivalence modules. So you have the Riffel correspondence, and the Riffel theory tells you that you get the dual homeomorphism, and also the periodicity when A is simple is equivalent to outerness in this sense. So all this example transfers to Hilbert modules, to these abstract actions of modules. And we want to define the periodicity for inclusions. So here is the definition. Definition is short. So if you have this inclusion, then you may view B as a bimodule, and this descends to this Banach A bimodule for the quotient. If you take the quotient of B of A, which makes the definition even more complicated because then you need to use the norm about this quotient norm. So that's annoying, but if you like this to have these conditional expectations, and we eventually will have one, so then this simplifies. So if we have a conditional expectation, then this quotient is naturally isomorphic to the kernel of E. So usually when you have like a map, you know that the range is isomorphic to the quotient by kernel, but the opposite also somehow holds. So this is the quotient by the range of E. Then this is isomorphic to the kernel. So then this conditions just means that we can avoid this quotient norm, but we need to restrict only to elements sitting in the kernel.
Is A still, A and B still simple?
No, so this is like a general. So I just learned it recently that Osaka used this condition to define a conditional expectation that he called outer. But as you can see, that this does not depend on the conditional expectation. This just depends on the inclusion. So in fact, this is a property of inclusion because this condition is equivalent to inclusion. And Osaka also, in his paper, proved that another very essential property, which is also technical, but to people who work with this stuff, this is very familiar. And Rodin even gave it a name, so he called this pinching property. So whenever we have this funny technical condition, we get another one funny technical condition. So this condition tells you that this conditional expectation, at least up to norm, can be obtained by compressing with some positive element. So you can compress this AB by this A to something which at least in norm is close to AB. And this is enough to prove these results about the ideal structure and pure infiniteness. In fact, this condition could be added to the list from the previous slide, and this would be also equivalent condition.
Wait, just quick naive question. So if you take your A to be the fixed point algebra by an action on the sister algebra and B to be the original sister algebra. Okay, what can you say about the sister irreducibility?
So is the group, for instance, abelian? Then if you have the fixed point algebra, then this is a reduced sister algebra of a full bundle, because then the spectral spaces for this action will give you the grading by the dual group. So if you have an action of a compact group, say compact abelian group, that will be perfect, because then you will get the grading will be given by the discrete group. So this is also maybe I should have given you this example of a grading which doesn't come from the cross product. Would you like to have that? So my favorite one is the Kunz algebra. So I recall that the Kunz algebra is the sister algebra generated by n isometries that satisfy this Kunz relation. So the ranges sum up to 1. And this is a very known and basic and important object. This is the course of algebra. So the course of algebra is in fact span of what? Of all these guys, S mu, S eta, star, where these are given by words, and then the length of these words is the same. So S mu is just S mu 1 times blah 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 S mu n, where mu is a word. Maybe I should not use n, and it's fixed. Maybe I should use m. Mu 1 blah blah blah. And then this is a core. This is the fixed point algebra for the circle gauge action, and then this Fn is this inclusion is system irreducible, and in fact all the conditions that appeared here apply to this. You have everything what is written there, and like I said, this grading here grading is by Z, because this is a fixed point algebra for the circle action. So the dual group is Z, and so maybe I should write even VK. So that this would correspond to this group grading. So these are like defined like this. These are spectral subspaces. So we have S mu, S beta star, but the lengths of these words differ by K. K here can be anything. So these fixed points of group actions, yes, they are another source of examples of this type. Yes, that's true. That's a good point. Okay, so this is a periodicity, bon, very, very technical, but yeah. And okay, so this holds when you have a conditional expectation. And let me make a detour to one slide detour to the world when we don't have expectations. I mean, when we don't have a conditional expectation. So this requires this notion of injective envelope of Hamana. So this is a sister algebra that contains A, like the smallest sister algebra that contains A, but is injective in the category. I think we can stick to a category of sister algebras, but the maps are completely positive maps or completely contractive maps. I think it doesn't really matter. You get the same universal object. This is this. EI, EA, IA. And this injectivity gives you immediately that this inclusion, I mean, the inclusion of sister algebras is a perfect embedding in this category of completely positive or completely contractive maps. And by injectivity of A, it expands to a map from B, not from B to not into A, but into I of A. So this is something like more general than the conditional expectation, because here the range is not in A, the range is only in I of A, and A is 6 in I of A. So the range might go outside of A. But the benefit is that it always exists by this injectivity, by this universal property. And so recently also people started to study these, especially David Pitt. So one nice result due to Pitt and Zarikian tells you that if you want to have this detection of ideals in or intermediate system algebra, so these are those defined there, so this detection of ideals, this holds even only all pseudo expectations are faithful, meaning they do not kill non-zero positive elements. So this is especially nice when you compose this with what we proved with Ralph. So we proved that if our inclusion is aperiodic, then it admits a unique pseudo expectation. So we have just a unique expectation. So in order to have this detection of ideals, you need to check only faithfulness of this one. But we also proved something more. So we proved that this faithfulness, I mean, under the assumption of aperiodicity, is equivalent to support of ideals. This is the stronger property that I told you. So support implies detection, but detection implies faithfulness of this by Pitt and Zarikian. So this gives you already some equivalences in our main theorem. And I'm not sure if I should talk about that. So do you want me to talk about this? Maybe I should talk about these group weights. So group weights are nice examples where when there's a conditional expectation does not exist in general. So let's consider this ethyl groupoid with twist, but maybe you may forget about the twist. And the space is locally compact Hausdorff. So you've heard a talk by Jonathan Taylor, I guess, and this essential blah when he talked about these non-Hausdorff groupoids. So this condition just implies that the groupoid is locally compact and locally Hausdorff, not Hausdorff in general. So what is a periodicity then? So then you construct the system algebra, the reduced system algebra of the groupoid, and the algebra of functions living on the unit space sits there as a sisters of algebra. So this inclusion is aperiodic if and only if the groupoid is topologically free. And what does it mean that it's topologically free? This means that for every bisection that leads outside of the unit space, the set of this is the isotropy group. Maybe I should draw a picture because I'm not sure how many people here remember the stuff about groupoids. So we have a unit space, this is X, and we have arrows here that are invertible, and these arrows form the group weight. So what is a bisection? The bisection is a set of these arrows where the range and domains of these arrows, I mean, are injective maps. So maybe I should write like domain or source of U, and we have a range of U, and we have a bunch of arrows here, and this set of arrows form this bisection U. And so for any point here, there is a unique arrow here that starts in this point. And for any point here, there's a unique arrow that lands in here. So this means that any bisection U here give you a partial homeomorphism. These are open sets. This is an open set. So these are open sets. This give you a partial homeomorphism on this X. And this requirement of topological freeness just tells you that the set of fixed points for this partial homeomorphism have empty interior. So this is a periodicity. So this implies, for instance, that if we have this unique, pseudo expectation, and if it is faithful, then we have all these nice properties. But so whenever the group weight G is Hausdorff, then we know that the restriction. Give you a usual genuine conditional expectation, because if G is Hausdorff, then this unit space is not only open but also closed subspace of G. So we view it as a subspace of the group weight. So in the Hausdorff case, this is compact open, closed open set. So restricting continuous functions to closed set give you a continuous function. And in no Hausdorff case, this is no longer closed. So in general, what you have that this restriction give you a generalized conditional expectation not into C of X, but rather B of X or D of X are bounded Borel functions. But this algebra is not contained in the injective envelope of H. A is here now C0 of X. So in order to have the pseudo expectation, we need to mod out this B of X. So we divide the space of bounded Borel functions by the set of bounded functions that are supported in Niger sets. And so this is a nice sister algebra. This is called Dismir sister algebra because Dismir was the first to consider this. And luckily, this algebra is exactly this injective envelope of our commutative sister algebra. So this was, I think, recognized by several people. So we always have this pseudo expectation. So we have these nice properties, even only if the pseudo expectation is faithful. Unfortunately, not always it is faithful. I mean, when the group weight G is Hausdorff, it is faithful because we don't need to mod out by anything, because we land up in continuous functions. But in general, we need to mod out something if we want to have a faithful map. So this is a pseudo expectation, but in general is not faithful. But if we pass to this quotient, it descends to this quotient, and then it is faithful. So this quotient is what we call the essential group weight. So this is just a digression.
I have another question. So you can say, for example, that the inclusion is aperiodic. If and only if it's topologically free, that there is no obscure sets or bisections. But what if you, for example, flip this around and say you have a non-aperiodic inclusion, so that there is some open bisection with this property that it has empty, isotropy subgroup of it, or I don't know, the intersection with this has a non-empty interior. Can you construct an ideal? So I'm thinking of like you mentioned before, the inclusion is aperiodic if every intermediate C star is simple or something like this, or if it detects ideals or something like this. So that in this case, can you maybe construct some special ideals? So the same way, for example, you take invariant subsets, of your unit space, you can construct always these ideals, right? Can you also construct something
Yeah, I
else in this
mean,
case?
so I'm not quite sure that this is exactly what you want to hear, and I did not want to talk about this, but the periodicity implies there's generalized version of detection of ideals. So whenever you have this A, B is aperiodic. So you have this unique pseudo expectation from B into I of A. Then you will always take this n. So this n is the largest ideal in your system algebra B that is contained in the kernel of E. So E is just a linear map, so the kernel does not need to be an ideal. It's not an ideal B. So you take this n to be the largest ideal in the kernel, and it cannot intersect A. So intersection with A is trivial. So this means that this inclusion descends or factors, I don't know what's the right name to this inclusion, but you could call the essential inclusion. And here A detects ideals and A supports this. So what I want to say is that A supports. So you may always pass to this quotient. And where A supports your Bn whenever your inclusion is aperiodic. Is that related to your question?
I think not quite. So like I was thinking of, maybe let me rephrase it again. So when you have an invariant, when you have a subset of your unit space, an open subspace of your unit space, and if it is invariant, then this defines an ideal inside the group pointer. And I'm thinking so of something similar like for the isotropic groups. So if you have some sort of like can you construct an ideal the same way, like if you have some peculiar isotropy, and how would you define an ideal like related to that?
Related to a peculiar isotropy or just isotropy?
So like if you have an open bisection and you take the intersection with its isotropy.
Yeah.
And if
Like
you take
here?
its interior, yes.
Isotropy, I don't know what it is like. Yep.
And you take its interior.
Mhm.
And if this is non-empty, like or generally like just interior taking, how can you construct an ideal inside the groupoid algebra?
I mean, so there are a number of papers dealing with this kind of idea. So for instance, that you take this isotropy, whatever this non-trivial isotropy happens, you take the interior of the set and then you divide it out. So there are a number of papers by a number of people there. Usually you need to assume something. So for instance, the essential algebra defined by Excel repeats, this is the way they define it. They just take these elements where the isotropy is non-trivial and they divided this out. But if this has a non-empty interior, this means that they kill some functions from C of X. And this is too much. I mean, I can quotient B if I want to have like this property, but I don't want to quotient A. For me, A is like, I should not touch it.
Okay.
So, but I don't have more to say about it at the moment.
Yes, I think roughly I get some.
Okay, so I think I don't have much time to talk about this nice property, the almost extension property, so we'll just skip it unless you stop me. And I don't see anyone to stop me. So this is related to this topological freeness, topological principality. And maybe I will go right away to the result. I mean, I want to tell you how to prove that the theorem that I started with. So let's go back to these regular inclusions. Let us avoid this abstract blah. I mean, this is still abstract, but maybe less abstract. So we have these normalizers, and regularity means that these normalizers, they span the algebra B. And all the ideas behind this, I mean, are in fact included in this remark here. So, like I told you, this non-commutative Cartan algebra are modeled by inverse subgroups. Also, in this groupoids, this bisection, they form an inverse subgroup. And the fact that we have this inverse subgroup, I mean, it follows, I mean, this is hidden here. So let us consider the spaces that consist only of normalizers. So they are closed in norm, and then they are A by modules. So they are also closed by multiplication by the left and from the right by A. So there are plenty of them if we assume regularity, because whenever we take a normalizer, then you can easily check that then A, if you take the closed linear span of these guys, then this is an element of S. So these elements there, Rui Axel called them slices. So these are like non-commutative slices, because he also calls this in the groupoid case, this bisections, he also calls them slices. So whenever you define a multiplication for these spaces like this, for these bimodules like this, so in fact they are Hilbert bimodules with these natural operations coming from your system algebra B. So if you define a multiplication like this, like closed linear span, if you define the evolution like pointwise, then this becomes a semigroup, and this star gives you that this is an inverse semigroup. Inverse semigroup is a semigroup with this kind of strange involution, which means that this involution gives you a generalized inverse. So this holds for any m. And so also this means that also this holds. So this means that this is an inverse semigroup. In fact, these are spaces, and these spaces, because of regularity, span the whole algebra B. So the whole algebra B is given, spanned by the slices. And we multiply in that way, but you can think of this as inverse semigroup grading. So this means, without giving you much detail on what is a Fell bundle over inverse semigroup, but I hope you can imagine. So this means that these elements in S, in fact, they form a Fell bundle over inverse semigroup. And so there is a universal algebra for this. And this means that we have a surjective, natural surjective homomorphism that is identity on each of these spaces from this universal object onto B. And if you want to describe it as a reduced object, we need to impose some things so that this epimorphism is sent in isomorphism the reduced level. And this is how Rui Axel defined it. So he defined those non-commutative Cartan inclusions. So this is like in Renault case. So first, we assume that the inclusion is regular. Secondly, we want to have a faithful conditional expectation of the genuine conditional expectation from B to A. And with Renault, we Renault considered only the commutative case. I mean, when the A is commutative. And then he imposed, so he required A to be a maximal abelian subalgebra in B. And this could be written like this, but the communion of A in B is A again. So if A is commutative, this inclusion means that A is a maximal abelian system subalgebra of B. There are no other elements in B that commute with A. So you could use this condition because this makes sense even when A is not commutative. But as Rui Axel noticed, this is not enough to get this nice characterization of your Cartan inclusions by some full bundle sister algebras. So he introduced this notion of a virtual commutant. So look, whenever you have an element in here, whenever you have M in here, then you may define this map. And it is defined on whole A. So you may define this map from A, this M from A to B in an obvious way. So you take and multiply it by M. So whenever this M commutes with A, this map is an A by module map because you can move this M around. So any commutant here will give you the virtual commutant in the sense of Axel, but he just requires to consider the maps, and also he requires to consider the maps that are defined only in an ideal. So having defined this, to prove that then any non-commutative card inclusion comes from inclusion where we have this isomorphism for the reduced sister algebra associated to a fell bundle over inverse semigroup. So then we improved it with Ralph. So we characterized which fell bundles give you these non-commutative cardinal algebras. So here is a very quick view of this main result on non-commutative cardinal subalgebras. So we assume that A is this inclusion is regular, you have a faithful conditional expectation. So then this lack of virtual commitants. Oh, I didn't say what does trivial mean, but it is written there. So it is trivial when M is in A, then this guy takes values in A. So we also require this for this virtual commitants. And this is equivalent to for this kind of compressed inclusions for any ideal to have at most one conditional expectation for a number of conditions, but maybe with those. There is this notion, I mean, so there's a for any ideal, we need to have this competence of I has to be trivial. I mean, they have to sit in I, so then they have to sit in the center of I guess. And then the B is isomorphic to a full bundle over inverse groups, the purely outer. Purely outer means like outer, but we need to have outer and also when restricted to all ideals, invariant by a fixed fiber. So I don't want to get into details unless someone is interested. So I just will switch quickly to the case where A is simple because we are interested in sister irreducible inclusions. So when A is simple, fits are simplified, so there's only one ideal, so this condition simplified, and most of all, this condition simplifies. So the corollary is immediate. So when we add this assumption that A is simple, then this inclusion is not committed to a term, if and only if this has a unique conditional expectation. So this uniqueness can be, so this is irreducible. I told you that in general, this irreducibility is not enough for system reducibility, but in this case it is. And this is just outer because there are no ideals in A, so we don't have to pass to purely outer. And moreover, this inverse sum group here is in fact a group, and this also follows from simplicity of A, because these relations will tell you that each of these guys is an ideal in A. But if A is simple, this means that they have to be equal to A. And A is a unit in our inverse sum group. So this means that this inverse sum group is in fact a group. And this gives you this nice description by just fell bundles over discrete group. So in this picture also the fell bundle and the group is uniquely determined. And since, like I told you, outer Hilbert modules are periodic when they are over a simple algebra, then this means that these inclusions are automatically periodic. And this means that they are sister reducible because of properties of a periodic. So this is, in a sense, one way. I proved this theorem. I don't know what I proved. I proved a number of applications, but so in particular, I didn't prove what I didn't prove. I mean, this implication is trivial. So whenever you have a sister reducible inclusion, then A and B has to be simple because every intermediate sister algebra has to be simple. And this inclusion has to be reducible, meaning in that there are no non-trivial commitants. And the converse implication is false. And these are those examples come from these inclusions of the group into a cross product rather than the algebra where the action takes place into the cross product. So that is why these inclusions cannot be regular, because if I add regularity here, then I have this if and only if condition. So this is the lacking implication for the proof of this main theorem that I started with. So if I assume that my inclusion is regular, irreducible, and A and B are simple, then this inclusion is sister reducible. So regularity here is crucial. And here's the proof. Since A is simple, the slices form a full bundle of a group. So this is what I roughly explained here. And so then this regularity gives you that we have this epimorphism from the universal algebra to B. And then irreducibility, in fact, just means that there's a full boundless outer. And this is easy to see. And outerness is aperiodic because we assume that A is simple. And this periodicity implies this generalized detection of ideals. So this means that this algebra B has to lie between the universal and the reduced object. So this natural epimorphism that compose to the regular representation. And since we assume that B is simple, then this epimorphism has to be injective, so this has to be a isomorphism. Okay, so I don't know whether I can reduce this assumption of simplicity of B, but I'm not sure. So this is the last slide. So I come back to my theorem, my main theorem. I mean, so these are some of the properties I mentioned. So once again, I have a regular sister inclusion with a small algebra to be simple, then the following conditions are, well, this is what I explain now. So the inclusion is sister reducible. A supports all intermediate sister algebras. So this is a stronger property than detection of ideals. A is a periodic inclusion, and the necessarily unique pseudo expectation is faithful. This necessarily unique pseudo expectation is in fact a genuine condition expectation. We have this irreducibility plus B simple. And this is equivalent to being non-committed Cartans of algebra in the sense of Excel. And we have this outer full bundle. And if the above holds, then there's a full bundle group or unit determined by this inclusion. So in this way, we can think of this inclusion as a dynamical object. And just to finish, I have this conjecture. So if the above holds, it should be true that every intermediate sister algebra is given by a subgroup of this group G. So whenever you have a subgroup of G, so it's like in this product case, then there's this full bundle restricted to the subgroup. You can also form the reduced sister algebra of it, and it sits naturally in B. So every sister algebra like this is an intermediate system of algebra. But the converse is, I don't know, I mean, this is not an easy fact to prove. So for finite groups, this was in fact proved by Zumi under the assumption that A is sigma unital, I think. And for cross products, the unital A, this was proved by Cameron Smith. But we need to somehow go to this more to this one step to consider these more general actions of by Hilbert modules to full bundles. And for this, I don't know whether this is true. So whether we have this Galois correspondence between these intermediate sister algebras and subgroups. So maybe I should stop and wait for questions if there are any.
Great, thank you very much for the nice talk. Are there any questions?
Can I just check so these relations? Is it really M star M is M star, not M? Ah.
Yeah, you're right. That's a good question. And the answer is no. I mean, it was no, but now it's yes. So the problem here, I will ask myself a question. So why is that? I mean, the problem here is that if we can prove that every intermediate sister algebra, I mean, but every intermediate inclusion is regular, then we are done. Because then we can apply the same theorem to A and C, and then we would get this Galois correspondence. Another way to approach this would be via this Morita equivalence, because every full bundle is Morita equivalent to this genuine action by passing to this double cross product construction. But if you stabilize this, if you go through the Morita equivalence, you immediately land in algebras that are non-unital. And their proof is for unital A. If I had a proof of this theorem without unital unital assumption of being unital here, then I could use this Morita blah as a general machinery to get this result. But I don't have this. So these are kind of annoying things that are lacking here.
I think it's plausible to extend the result in non-unital way, or
I mean, so when you look at the vector root, which is kind of involved, there are also people like coming from polynomial algebra, we use all these polynomial algebra techniques, and they use this unitality a lot. So it is not clear for me. So you see, when A is simple and unital, then you have this nice property that whenever you have a non-zero element, whenever you have a non-zero positive element here, then you may find those elements in your A such that this is a result. I mean, this is a fact known lots a lot, used a lot. So then it's bigger than what when you have a unit in A. So when you have a unital simple algebra, then you can do lots of things like and then using this result, for instance, this fact. This is like a fact from several textbooks. And in non-unital case, you already don't have that.
But saying it's strongly mixing in itself.
Yeah, this is like strongly mixing. Yeah, it's strongly mixing itself when it is simple and unital.
Well, plausibly, you could think of just, in the non-unital case, you'd want the sum times some element B.
Yeah, you want that, but can you prove this? That's another question.
Maybe you would want. But
I mean, to tell you the truth, I didn't think hard on this question.
Yeah.
I think this is interesting, and I just started looking at this like recently. So I am quite ignorant, so maybe there's someone who knows the answer already, but yeah.
I mean, maybe so A is simple here.
Yeah.
So maybe you would want like algebraically simple in non-unital case.
Yeah.
Something like that.
Yeah, so in unital case, there's simplicity, this analytical simplicity gives you like an algebraic one, but without a unit, I don't know, how is that? Who knows?
Yeah. I mean, you can always pass the hereditaries of algebra to get something that's algebraically simple. But I mean, I'm just saying things. I don't know.
Yeah, keep on saying. Yeah, so maybe with an assumption that algebraic simple, but is it the same? I don't know. Yeah. Otherwise, thank you for your patience.
Can I have another question? Can you hear me?
Sure, Karen, can he ask another question?
So
Yes, you
related-
can.
Okay, so related to the discussion, like can you? So if you flip the perspective and say, for example, if you don't have this, like, do you know some examples, like if you don't even have like one of the following conditions, or like if you drop simplicity, can you have like some? Do you have some intermediate algebras that are? Do you know some examples of intermediate algebras that are not given as by some subgroup, like by some fair bundle, restricted to some subgroup? Do you know some examples like that?
Yeah, I mean, I know examples of micro-Rodham, like those there. They are not regular because they can't be, because they would contradict the theorem. So he constructed for any sister simple group G, he constructed an action on this, all infinities is this Kunz algebra generated by infinite number of isometries, such that the cross product is simple, the group is sister simple, so that the reduced sister algebra is simple. This inclusion is irreducible in this von Neumann sense, but it is not irreducible in the sister algebraic sense.
But do you know that, like, so do you have an intermediate algebra that is not where you know it cannot be the section algebra for a fell bundle, for your fell bundle, like restricted to a subgroup?
So this is related to this Amrutan's work. I don't have a slide for this, but he considers also these inclusions like this, but which are system reducible, and then you can, I know, but then they are cross products. Okay, you want to have an inclusion, but that the intermediate algebras are not cross products of some sort.
Yes.
This is what you want?
Exactly. Like an example like this,
Um,
where you know it's
I mean,
like
if you think about cross products in a very general way, then all of them would be some cross product, but I don't know. I don't have a
no,
good
like
example.
yeah. So your B is given by some is given as the like the algebra for a file bundle over a group. So like BGs. And where you have some of the assumptions not satisfied, and where you know that where you know some intermediate algebra which cannot be the C star algebra for your file bundle restricted to a subgroup.
Mhm.
Like,
I
do you
think
know
that
some
should
example
be,
like this?
that should be easy to come up with. But I don't have a good example at that point. But I think that that should exist like a lot.
Okay, yeah. Thanks. Anyway,
Yeah, thanks.
Yeah, quick question. So is all this stuff on the archive yet, or is it still?
I mean, so no, I mean, no. So I mean, I talked to Mika Roda, and yeah, I told him, you have this paper, and then you prove some things, and most of this follows from my work with Ralph Meyer, and he said, yeah. I mean, he wrote it, so no, in his paper, and then because I maybe didn't make effort to explain these things to people, so I just started doing this now. So this is not an archive. In fact, I mean, there's nothing to put on. Maybe I should put on archive just a note, but I don't think that this should be. If I can prove this conjecture, for instance, then I can like write an article. But otherwise, there should be like just a note for people to know about this. And maybe there is a reason to write like 2 pages notes. You put it on archive, maybe because the only piece, everything is there, but it is spread around different papers. But the only piece is this proposition. This is the only missing piece for having these equivalent conditions. And this is easy peasy.
Always easy to know how.
Yeah, that's true.
Okay, so if there's no more questions, then let's thank the speaker again. Right. Well, yeah. I escaped. Oh, okay. Coming over here to say, thanks, bye-bye.